Particle or electromagnetic? Yes, particle. What about positrons? Yeah, particle. Now the nuclide symbol is how we can identify that type of radiation in a nuclear reaction. So here are the nuclide symbols. So note that you have the symbol here, E or HE or N, and there is a superscript, a subscript. So the superscript is the mass number. The subscript is the atomic number. So we take a look at this one. Helium 2 plus is the charge. The 4 represents the mass number. So we look at the periodic table. Note that helium has a mass number, or can have a mass number of 4 for one of its isotopes. Helium also has an atomic number of 2. So for this one is the nuclide symbol for which type of radiation? Alpha, beta, X-rays, gamma, neutron, positron. Yes, it turns out that this one here is a nuclide symbol for an alpha particle. Okay, so really alpha particles are really just a helium nucleus. What's the nuclide symbol for a beta particle? So you're saying is it the first one, second one, or the fourth one? Yes, the second one here. So note that the E means it's an electron, so a beta particle is just an electron. And the -1 here, although we know that an electron doesn't have an atomic number, the -1 here tells us the charge on that electron. Okay, also we're telling that note that an electron mass is very, very small, so we're saying that the mass will be 0. This is a nuclide symbol for which type of radiation here? Positrons. Yes, for positrons. Note that a positron is actually a positively charged electron. So if you believe in matter and antimatter, note that an electron and a positron are examples of matter and antimatter. Then for a neutron, what's the nuclide symbol for a neutron? Yeah, so this one here. So this is the nuclide symbol for a neutron. Note that gamma rays and X-rays are a type of electromagnetic radiation. So for a gamma ray, you may see this in a nuclear reaction. Okay, for a gamma ray. Okay, so this is a nuclide symbol for a gamma ray. I haven't seen a nuclide symbol for X-ray, so I'm not quite sure what that one looks like. Okay, let's keep on going. Where does radiation, before we go on, I forgot to mention the source. So, where do alpha particles come from? It could be from the sun. So it could be from the atmosphere. So what substance specifically will produce an alpha particle? Can you name a substance? Yeah, so for example, in a nuclear power plant, they use uranium-235 as a nuclear fuel, so alpha particles are actually produced in that nuclear reaction. What's one source of a beta particle? Okay, so one source would be, for example, carbon-14. Okay, so carbon-14 is one isotope of carbon. That will produce a beta particle. Where do X-rays come from? So, for example, you get X-rays at the dentist's office, or your doctor takes an X-ray. What are the source of X-rays? You ask your doctor that next time you get an X-ray. See if the doctor knows. Yeah, so it could be, for example, iron or molybdenum. Okay, so there's an isotope of iron that will produce X-rays. What about gamma rays? Yeah, so gamma radiation is used in medical therapies. Have you heard of gamma knife surgery?
Oh, yeah.
Yes, actually for gamma knife surgery they actually use this technetium. Technetium-99. Okay, that's what gamma is.
Can you repeat that?
Technetium. Neutrons are another source. In the 1980s, near the end of the Cold War, the military produced the neutron bomb, and they said that the advantage of the neutron bomb is that it kills people while leaving buildings and structures behind undamaged. That was sales. That was in the 1980s.
Was it
I'm not sure they were.
That's not part of like the nuclear bomb thing. If you're in a building and it crashes the building, it's going to kill you.
So can you name a source of neutrons? Yeah, so what's in the neutron bomb? Yes, I can also tell you that, for example, in a nuclear reactor used to produce energy, the uranium, which undergoes that nuclear fission reaction, also produces neutrons. So that's one source of neutrons. And then for positrons, another medical therapy is polytron emission, PET, polytron emission tomography. So one source of positrons is actually a sodium isotope. I think it's sodium-22. Okay, so based on that, where does radiation come from? So remember, we asked a similar question in Chem1A when we said, where does light come from? And remember the answer to that question, where does light come from?
The sun.
Where do electrons come from? Where do you find electrons? The atoms. So light comes from atoms, molecules. Where does radiation come from then? Nucleus, which means that comes from atoms and molecules. Okay, so here's some sources of radiation. So this is the annual exposure per capita in the U.S. in millirems per year. So for natural background radiation, for example, from the ground, from ourselves, 130 millirems per year. For medical x-rays, 90 millirems per year. From weapons tests, fallout, although they haven't tested weapons in 50 or 60 years, still about 5 millirems per year. Nuclear power plants, less than 0.01 millirems per year. So note that, what do you think is the largest external source of radiation?
The environment.
Yep, the environment. So this could really just be from the ground. Note that on Earth there's minerals which contain a radioactive substance. For example, uranium actually comes from a mineral. Okay, so we get a lot of background radiation from uranium. An internal source of radiation is from our body. So for example, we have a lot of potassium and carbon from our body. Part of the potassium and carbon come from, one of the isotopes of potassium is a radioactive isotope, potassium-40. Same thing for carbon. We have a little bit of carbon-14 in our body. So those are the two sources of internal radiation in our bodies. Okay, then we'll take a look at some units. So unit of activity is the Curie. This tells us how many disintegrations of radioactive nuclei occur per second. Röntgen was a famous physicist who studied radioactivity way back in the 1800s. It's a measure of X-ray and gamma ray ionization error. The Röntgen equivalent physical, or called the REP, that's the measure of X-ray, gamma ray, and particle radiation. The radiation absorbed dose, or the RAD, is the energy in joules per kilogram of tissue. Now here's the REM. The REM is the radiation absorbed dose times the RBE, which is the relative biological effect. Now the RBE depends on the radiation type and the relative penetrating power of that radiation type. So the greatest penetrating power comes from X-rays and gamma rays. the least penetrating power comes from alpha particles. The highest relative biological effect comes from alpha particles because that's the type of ionizing radiation. The lowest RBE comes from beta particles and X-rays. So it turns out that there's actually a table in the textbook. I think the alpha particles, for beta particles and X-rays, the RBE is 1. For alpha particles, I think the textbook says it's 20. So note that alpha particles are 20 times more damaging to human tissue, actually any organism, than beta particles or X-rays. Okay, so is radiation dangerous? And if so, what should we do to protect ourselves from radiation? Yeah, so for solar radiation, what's the radiation type? Yeah, so for the most part, when the sun gets to the surface of the Earth, is the radiation going to be from electromagnetic or from particle radiation? Yeah, electromagnetic. So how should we protect ourselves from the sun's rays? Yeah, just use sunscreen. Or actually just wear clothes. Now for the CT scan involves X-rays. X-rays involve what type of radiation again? Yeah, electromagnetic. So what kind of protection do we use for X-rays? Yeah, lead shield. Now, a PET scan is from positron emission for tomography. So, how should we protect ourselves from a PET scan? Positrons. Yeah, you actually don't need something as like lead. You can actually something less dense. You can actually use something like paper or aluminum foil for that. For carbon-14, which is a beta emitter or electrons, the same thing. Paper or aluminum foil will protect them from electrons or beta particles. Alpha particles, for example, from U-235, what is needed to protect yourself from an alpha particle? Yeah, so you'd expect, although alpha particles have the largest or the highest RBE, alpha particles are stopped by the skin. So it doesn't take much to stop alpha particles. The problem is if you ingest or inhale something which is an alpha emitter, it gets into your lungs. We'll talk about that next week. MRI, magnetic resonance. So what type of radiation is involved in MRI? Yeah, so for MRI, it's actually radio waves. Yes, it's a magnetic field. There's also, and then the transitions which occur are picked up in the radio wave frequency of the electromagnetic spectrum. So you actually, for radio waves, as long as it's not in the region you can hear, then I guess you're okay. What about gamma rays from technetium-99? Yeah, for that you need concrete. And for ultrasounds, sound waves. And for that, what do you need? Yeah, you're actually fine. We're really affected by sound waves. Radioactive means radioactive isotope undergoes radioactive decay. This list tells us which isotopes are radioactive. So if the atomic number is greater than 83, all the isotopes of those elements are going to be radioactive. In general, if there's an odd number of protons and an odd number of neutrons, chances are that isotope is going to be radioactive. If there's an even number of protons and an even number of neutrons, chances are that isotope is going to be stable. Okay? And then there's also what's called the band of stability. There's a band of stability diagram in the textbook. So if the isotope is within that band, it's going to be stable. If it's outside that band, it's going to be radioactive. Then they call these magic numbers. And the magic numbers, there's this shell model of the nucleus, similar to the shell model of electrons. We're looking at electron shells. So if an isotope contains the magic number of protons and neutrons, chances are it's going to be stable. Okay, I'll let you know what those magic numbers are next week. So let's just do this as a review. how many protons and neutrons are in carbon 14? Okay, so here's carbon 14. So this is the mass number, and then this is the atomic number. So based on those two numbers, how many protons and neutrons are in carbon 14? Yeah, so the 6 tells us the number of protons. Okay, so there's 6 protons in carbon 14. How many neutrons are in carbon 14? 8. So the number of neutrons that's equal to the mass number minus the atomic number. Okay, so there's 6 protons and 8 neutrons in carbon 14. So carbon 14 is actually one of the exceptions of this odd protons, odd neutrons rule. You're going to be looking at potassium 40.